Okay, we're back. We're talking rotational motion. And in particular, I wanted to introduce what torque is and how we can find how strong a torque is. Torque is to rotational motion what force is to linear motion. So we know from F equals ma that if you have a net force acting on anything, it's going to cause an acceleration, a change in its linear motion. Either speed it up, slow it down, and or change the direction that it's moving. Well, we have the equivalent of that in rotational motion, make things spin and rotate. But what's weird about it is that force by itself is not enough. And I can give you some examples of that. Imagine if you had a bike turned over and the wheel is just there. It can't move linearly. All it can do is spin. If you were to push on the edge of the wheel, like I'm drawing here, where it's parallel to one of the spokes of the wheel. Okay, now notice what I'm calling the axle in the center. We're calling that the axis of rotation. That's our reference point for everything that we do with rotational motion. But yeah, if I push or pull along the spoke like that, parallel to it, it actually won't spin. Okay, so we're applying a force, but there's no rotation. What do you have to do to make it actually spin? Well, you could, instead of pushing along the spoke, what if you pull on the edge of the wheel? Maybe like pull it down or something like that. When you do that, pull down on it or push on the spoke in a downward direction, then it spins. Okay, so it's a combination of the force and the angle between the force and that radius line, the spoke of the wheel. Now we can imagine, let's say, what if you were to apply a force right on the axle of the wheel? What if you push right on the center, okay, on the axis of rotation? That's not going to make the wheel spin either. So it seems like you have to have some distance between that axis of rotation and where you're applying the force, and you have to worry about the angle between the force and that spoke, okay, the radius of the wheel, in order to make the thing actually rotate. So that combination of those three things is what we call torque. Okay, so definitely need a force. That's still going to be part of it. But now we need a distance from where we apply the force relative to where the axis of rotation is of the object you're trying to rotate. But the third piece is you also have the sine of some angle. Okay, the angle between the radius line, drawn from the axis of rotation out to where the force is being applied, and the line of force. If they're parallel, it doesn't spin. If you have some angle between those two, it will spin. A torque will be created by that force. So this definition we're going to be using over and over and over again. Without torques, without a net torque on something, there won't be any rotational motion or any kind of angular acceleration to the object. Now, technically, torque is a cross product. Okay, that's something that for now, at this level, we don't really do much with. I just wanted people to be aware of that. 99% of the time, we're just dealing with the numbers, like how strong is the torque. And that's where we're going to be using this definition, this little formula here, in order to find out how strong torques are. Best thing to do is to look at some examples. Let's see how to apply this new definition for torque. So let's do some examples of wheels. We have a few forces on the blue wheel here. Well, in the case of the force acting on the center of the wheel, on the axis of rotation, the R value is 0. Okay, there is no distance between the force and the axis of rotation, so no torque. On the other hand, just like what we were talking about, this other force on the right, that's parallel. Now you have a distance between the axis of rotation and where the force is applied. It's the full radius of the wheel, but the sine of the angle, okay, the sine of 0 degrees, if they're parallel, means that there's no torque. If we hung a weight, like down at the bottom, so if you have like a tension pulling on the wheel, but that's parallel to that spoke, parallel to the radius, again, that one's not going to make it spin. no torque. That force on top, though, well, it's a full radius away from the axis of rotation, and it's a 90-degree angle between that line of force and the radius line. So that does produce a torque. Torque is a vector, it turns out. So for us, in a very practical way, we can look at that picture and say, okay, well, if I pull on that to the left, it's going to make that tire spin counterclockwise. So we can define whether a torque makes something spin clockwise or counterclockwise. That's the practical way of doing it. It's a little bit different when you do the cross product in something called the right-hand rule. But for us in problem solving, clockwise and counterclockwise is what we'll do. Notice in the middle wheel, those two forces are both creating torques. If let's say the forces are equally strong, it turns out the torques will be equally strong because both of these are at the edge, like on the rim of the wheel, so a full radius away from the axis of rotation, and they're both making 90-degree angles with their spokes, okay, with that radius line. So numerically equally strong. But if that's all we had, notice they're in opposite directions. That force on top is trying to make the things rotate clockwise, whereas on the side, that force going up is trying to spin the wheel counterclockwise. They would actually cancel out because they're in opposite directions. Now, if you hung a weight on the spoke, let's say, if everything's just at rest, then the tension would just be the weight. So that's your applied force. If it's in the middle of the spoke, that's only half a radius away from the axis of rotation, and it's making a 90-degree angle. So that would create a torque. Okay. The third wheel, let's say you're hanging something off the edge. Now notice that physically what's actually attached to the wheel is the string. So that whatever the tension value is, that's the force that is creating the torque here. And if it's just hanging straight down off the side, it's a full radius away from the axis of rotation, which is at the center of the wheel. It's making a 90-degree angle. And so, yeah, that tension force is creating a torque and would actually make that thing start to spin clockwise. You could imagine, if you had like a meter stick or something, let's say you nail it to a wall, so like a little hinge, and so it can rotate. Okay. On this first stick, notice this first force is acting right on the hinge, okay, right on the axis of rotation. No torque for that one. The R value would be 0. Now, for something like this, if I nail down one of the ends of a stick, the weight of the stick is at the center of mass, and usually right at the center of the stick. And that could cause the stick, if I let go of it, gravity can make it rotate. Okay, the weight, its own weight, is causing a torque on the object. And it would be half the length away from the end where the hinge is, and it's a 90-degree angle. So we calculate how strong that torque is. That force on the end of the stick, well, that's a full length away from the axis of rotation. And in this picture, it's a 45-degree angle between the line of force and the stick, which would be the radius line right there. And that would be the strength of that torque. Notice the weight is trying to spin you clockwise. If I'm pushing up on the stick on that right end, that's actually trying to make it spin counterclockwise around the hinge. So your net torque, we'd have to subtract those two because they're trying to make the stick spin in opposite directions. Okay. The last example here, that stick, again, the weight of the stick is half the length away from the hinge, trying to make it rotate clockwise. And the applied force is halfway, okay, at the midpoint of the stick, so half the length from the axis. And if it makes a 30-degree angle, we'd have to include the sine of 30 in order to figure out its torque. And that would be in the opposite direction again. It's trying to make it rotate counterclockwise. We have to subtract those. Last but not least is if you put like a ball on a hill. Now the two forces we know we're always going to have on a hill would be normal force and gravity. And gravity acts at the center of mass of objects. But for round things, if you let like a ball roll, the axis of rotation is also right at the center of the ball. So in most cases, the axis of rotation and the center of mass will be at the same location. It's the same point for like a ball or a cylinder or a disc or something rolling down a hill. Okay. But notice something with our definition, the weight, well, that's acting right on the axis of rotation. Gravity doesn't produce any torque for the ball. That's not going to make it roll or spin. The normal force, well, it's acting on the outside of the ball, but notice how it's parallel to that radius line from the axis of rotation to where the normal force is being applied. That's not going to make the ball roll either. No torque. So how does something roll on a hill? Well, if you put something around like on a sheet of ice, it's just going to slide like a block. It doesn't roll. You actually would need friction. Notice what friction does. You have a force. It's acting on the rim of the ball, the outside of the ball, so it's a full radius away from the axis of rotation. And the friction line of force makes a 90-degree angle with that radius line, okay, coming from the center. Friction creates the torque. That's what makes the ball actually rotate and roll as it goes down the hill. You need friction. So anyhow, here's some quick examples of how to apply this new definition for torque. Okay, how to find the strength of the torques. We'll be talking in terms of whether a torque is trying to make you spin clockwise or counterclockwise in order to find net torques. So hopefully this makes a little bit of sense, and we'll be obviously getting a lot of practice with it. Without torque, you don't have rotations. So yeah, but we'll be doing a lot with this definition and much more to come. So until next time, we'll see you later.